In this video, we talk about the coordinates and changes of bases. Let's recall some material from previous lectures. So given a vector space capital V and a collection of vectors V1, V2, etc., such that every element of capital V is a linear combination of those vectors. So in other words, we find a collection of vectors that span space V. And this set of vectors is called a spanning set. So if those vectors in a space V are linearly independent, they're linearly independent if none is a linear combination of the others. So equivalently, if whenever the linear combination is equal to 0 for some constants, all of those constants must be equal to 0. So the only linear combination which is equal to 0 is trivial. Another review of bases: a subset V1, V2, etc. of a vector space V is a basis for V if it is linearly independent and if it spans V. So to put it differently, a subset of a vector space is a basis if there is one, which means it's a spanning property and only one, so that the vectors are linearly independent, way to write any element from this vector space as a linear combination of vectors V sub I. So this is the most typical example people do in this case is this canonical basis in R3, or 1x and x squared is the basis of polynomials of degree at most 2, or the space P2. Now let's talk about linear transformations. If there are two vector spaces, capital V and capital W, then there's a function T from V to W is said to be a linear transformation if the following property is satisfied for all scalars C and C prime and all vectors V and V prime. Now there are two important cases of this linear transformation: when this function is onto and when it's one-to-one, right? So if f from x to y is called onto, if every element of y is an image, is f of at least one element of x. So there is one or more elements in x which are mapped to y, and we call it one-to-one if it's for every element of y, is at most is an image of at most one element of x. There could be none, but if there is one, there should be only one. So, and then as you can see, there's an overlap between them. So there's a one-to-one and onto if sort of these two statements are satisfied at the same time. Now, for linear transformation from Rm to Rn, we know that it's one-to-one if and only if the columns of the associated matrix are linearly independent, and it's onto if and only if the columns of the associated matrix span the codomain. Now, the easiest function is the so-called identity function, id(x), which sends every element to itself. So if x is a vector space, then id(x) is a linear transformation. And for Rn, it's represented by the identity matrix n by n. Invertibility. Another review. So a function from x to y is invertible if there is a function g from y to x, such that the compositions in both directions, they give identity operations, identity functions on x and on y respectively. So when x and y are vector spaces and f and g are linear, the matrices of f and g are inverses. So we can multiply them by one by another in any order, and we will be given the identity matrix in the corresponding vector space. Yeah, so as with matrices, if f has an inverse, it's unique, and we write it as f to the like f minus 1. So invertible linear transformations are also called isomorphism. So if there is an isomorphism f between V and W, we say that V and W are isomorphic vector spaces. So it's a kind of powerful, it's a powerful statement because isomorphic vector spaces look the same to linear algebra. Can be space R3 or space of polynomials of degree at most 2. They are isomorphic once you define the operations properly. So any question which you can ask in terms of operations that make sense in one space, they translate literally to another one. And the answer is the same in both, because some of the spaces they look more complicated than the others. So here's the following four statements are equivalent. The T linear transformation from V to W is 1-to-1 and onto. Then it's the same as it's invertible, and its inverse is also linear. Then T takes some basis of V to a basis of W, and it takes any basis of V to a basis of W, which is the same thing. So given a vector space capital V and basis Vi of this vector space, and vector space W with any elements Wi of W, there's a unique linear transformation, right, that takes Vi to Wi, right, and therefore it takes linear combinations to linear combinations. So for any elements Wi of W, there is a linear transformation Rn to W, right, which sends vectors from the canonical basis EI to Wi, such that, and then the string, the vector of scalars A1 through AN sends it to the linear combination with the corresponding vectors. So if Wi's form a basis in big W, then this map is an isomorphism. And we call this map a parameterization of W. So it parameterizes vectors in W by those coefficients. And the inverse map W to Rn we call a choice of coordinates on W. So the meaning of those two terms will soon hopefully become clear. Take an example, basis 1x, x squared, etc., x to the n of space Pn. It's I remind you, the space of polynomials in one variable with degree at most n. So as we discussed, it's isomorphic to Rn by n plus 1. Now, if you have a basis v1 through vn of a vector space V, we get a choice of coordinates v map to Rn. And then we'll use this notation V with subscript B, where B is the choice of the basis for the image of vector V under this map. So it's essentially for the vector V, we assign to every vector V, we assign a vector of coefficients, this string of coefficients from the corresponding linear combination over the basis vector. So if V is equal to some beta I Vi, then that's how this map works. It just gives you this string of coefficients beta 1 through beta n. So take this basis, as we discussed in the previous video, it forms the basis of P2, 1, x plus 1, x squared plus 2x plus 1 of P2. And then let's determine the image of this under this map of the vector x squared plus 2x plus 2. Now, which means that we need to find the coefficients C1, C2, C3 such that the linear combination of the basis vectors with these coefficients gives you the desired vector over here. Well, that gives a system of linear equations, which you can write like this. And we can solve them, right? So I hope you know by now how to do it. So it's the solution is 3 minus 5, 4. Now, a basis allows you to treat an arbitrary vector space, assuming it's finite dimensional, as if they were just Rn, and use matrices to parameterize them. So depending on the problem, one choice of basis may be more convenient than the other. So we want to be able to change basis at will. That is, given bases B and C of V, and given expressions V, B in one of them, we would like to find the expression V sub C in the other. So let's see how this works out. So we're looking for a transformation, which will be denoted with the symbol P, B goes to C, such that this transformation applied to the image of the vector B under the map B in basis B is equal to V in basis C. So it will be a matrix acting on this string of the coefficients, expansion coefficients of the vector V, and we should get the expansion coefficients of the vector V in the different bases. So it completes this triangle of isomorphisms. Every arrow in this triangle, in this diagram, is an isomorphism. So there is a map, parameterization map from V to Rn, and then there's a parameterization map to this is the choice of coordinates map from V to Rn, and the choice of coordinates map V to Rn with these two bases. And so these are the different choices of bases in V, and the map P B goes to C is it completes the triangle. So that's what we want to find. So it should be a matrix because it's a map from Rn to Rn, luckily. So in order to figure out which matrix it is, we need to see where it sends the vectors from the canonical basis, EIs. So take, say, B is equal to B1 through Bn, and C is equal to C1 through Cn. Now, this triangle of isomorphisms will map it as follows. So say we take vectors EI, the canonical basis in this Rn, right? And then we'll try to find the matrix. So this map acts on the, we pick, so one of the bases will be the canonical basis, which we'll pick in this copy of Rn, right? And then we'll figure out the entries, the matrix of the linear transformation, which changes the basis from B to C. So as you can see from this diagram, right, it takes you the acting on the canonical basis. You get BI expanded in basis C. So the ith column of this matrix is this vector is the expansion of vector BI in basis C. So let's, it may look a bit more abstract. Let's look at an example. So take B, the canonical basis in P2, 1xx squared, and C to be this slightly different basis, which are both bases, but yeah, so they look a bit different. So let's see how the change of basis matrix works out in this example. And then let's do it from C to B. So the columns of this matrix are 1. Well, these are the columns of this matrix, right? So it's 1b, x plus 1b, x squared plus 2x plus 1b, and we need to find those vectors. So as you can see here, so it's they're given by this easy triangular matrix. The matrix of the change of basis from C to B is given by this 1, 1, 1, 0, 1, 2, 0, 0, 1. So again, the columns of this matrix are coefficients of the expansion of each of those vectors in this basis over here. So as you can see, it's easy, like, it's easy to write this transformation once one of the bases is simple, like it's as easy as it can get. So in this case, it's the 1xx squared, which is somewhat analogous to the choice of canonical basis in Euclidean space R3. Now let's do it the other way around, right? So on the previous slide, we had change of basis from C to B. Now let's do change of basis from B to C. So it should be an invertible, it should be also allowed operation. So now we need to expand vectors 1, x, and x squared in this basis, right? So we need to find the coefficients such that 1 is equal to linear combination of this, x is equal to linear combination of those, and so on and so forth. Well, I hope it doesn't take too much time to figure it out. So 1 is equal to 1, so just 1, 0, 0. And then to get x in terms of this coordinates, you need to subtract this 1 from here. So it's minus 1, 1, 0. And to get x squared, to subtract 2x and 1. Yeah, so I mean, you can either, you can do it like, so x squared plus 2x plus 1. So you need to subtract twice this vector, so that gives you x squared minus 1 and add 1. That's why it's 1 minus 2, 1. Okay, so we see that these are the matrices, right? So we take the matrix of change of basis from C to B, looks like this. Matrix of change of basis from B to C looks like that. Well, you probably see where I'm going with this. If you multiply this matrices, you'll get well, maybe not surprising result that these matrices multiply by each other is equal to identity, since the changes of basis and then you change it back, right? So you should think of it as a consistency check. Yes, again, the matrix of the change of basis from B to C, from one basis to another, is equal to the inverse of the matrix of the change of basis from the second basis to the first one. So in Rn, it's should be very intuitive. So if you have, so let's say V is Rn itself, right? So now there's a triangle with 3 Rn's, and then there are 3 isomorphisms. So here you can see that these maps, the bracket B and bracket C, themselves are changes of basis, according to our definition. So we can write a standard or canonical for the standard basis, which is 1, 0, 0, 0, 1, 0, and so on. And then we have that, so we can identify those as change of basis from standard into B and standard into C. So it's easy to write the formula in the standard basis, right? Because V in standard basis is just V. It's you looking at the components of V and just writing them on a column. So as if you're just writing the vector itself, right? And then the matrix for change of basis from B into standard is B1, B2, and so on, Bn, right? So this is the expansion of vector B in standard basis. So to get the desired matrix, you need to invert it, right? So now you need to calculate. So this map bracket B would be the matrix of change of basis from standard into B, which is, by the previous discussion, amounts to inversion of this matrix over here. So we need to take this matrix and matrix of components B1, B2, and so on, and invert it to get the desired matrix. And same true for operation bracket C. And now you can compose them to find that the change of basis from B to C, matrix of change of basis from B to C, is equal to the product of matrix of change of basis from standard to C times matrix of change of basis from B to standard, right? So you feel like this standard should be in the middle, this index over here, and it's equal to matrix of columns of C's inversed multiplied by matrices of matrix of B's, and then the opposite matrix, the matrix of the change of basis in the opposite direction from C to B will be the inverse of that, which is given by this formula. So we can use this in order to, so say you want to change, so we use this as an intermediate step for here. So say I want to do the change of basis from B to C, and it's not immediately clear how to expand vectors from one basis in here as linear combination of vectors in other bases. So in the previous examples, it was pretty easy, but it's not always immediately possible. So we're doing an intermediate step. So we take the inverse of this map and then apply this map. Or if you want to go backwards, we do the inverse of C, bracket C, and then apply bracket B. That's how this works. So let's look at the composition. Say these are two bases in R2, right? B is 1, 2, 3, 4, and C is 3, 4, 5, 7. So let's just apply this formula, right? And that it's quite literally we're writing down those columns. So these are the components of the vector. So we go from vector from basis B to basis C. And then we apply them in the following order. So it's matrix of change of basis from standard to C times matrix of change of basis from B to standard, and you get this thing. So you take matrix whose columns are vectors in basis B, inverted, right? So you invert the matrix corresponding to the basis from which you are mapping, and multiply it on the left by the this matrix formed of the columns of the basis to which you are mapping, and you get this form. You get this matrix. So negative 3, 1, 2, 0 is the desired change of basis matrix. So if B is a basis in capital V and C is a basis in capital W, then the matrix of linear transformation T from V to W is written in coordinates by this matrix with indices T, C, and B, which completes the square. So say we have, so if the dimensions, now we have two vector spaces with different dimensions, possibly different dimensions. So there's a map for T from V to W, and then there are these maps bracket C and bracket B into the corresponding Euclidean spaces. So R to the power of the dimension of B, and R to the power of the W, and R to the power of the dimension of B. And this is the change of basis. The matrix of linear transformation written in terms of those coordinates is called TCB. So for a new choice of basis, B prime of V and C prime of W, we have this rule here. So we need to multiply the matrix of linear transformation from the left by the matrix of the change of basis from C to C prime, and from the right by the matrix of change of basis from B prime to B. So this way, the old basis will be, so the vectors from the old basis, they get convoluted with each other, and then the indices which remain are those with the C prime and B prime. Now, in a special case when those vector spaces are equal, isomorphic, and B and C are the same basis, we simply write T with index B. Now, and then if you have a new choice, if we change basis in this case, call it B prime, then the previous formula, given the fact that the B goes to B prime is the inverse of B prime to B, so we need to calculate only one matrix. P basis B prime into B and inverted, so the inverse matrix will multiply from the left, and the matrix itself will multiply from the right. So finally, for V equals to Rn, we have this rectangle of isomorphism. Now we recall that VB is the inverse of this matrix multiplied by vector V. So the matrix TB, matrix of linear transformation from R dim V to R dim V, is equal to T, and then which is multiplied from the left by the inverse of this matrix, and multiplied from the right by inverse of that of the matrix itself, and here it's the inverse.